speaker is Josh Lymburner from Crone. His talk is called The Routine In-House Use of Crone Borehole Pulse EM at Lalor. So Josh went to McMaster's University from 2006 to 2010 and received an honors in earth science degree. Following that, he went to Laurentian to complete his master's with Richard Smith, focusing on time domain EM. Since his completion and his graduation, he's been working with Crone Geophysics.
Thank you for the kind words. So, close enough here. So today I'm going to be talking to you about just some routine borehole EM surveys. So this data was collected by Dave Coop in-house with Hudbay. So I'm just going to be presenting the data. So I'm just going to briefly go and talk about the start of the story, which starts with the initial surface discovery. Just go through what it means to do some routine borehole EM. And once you get the data from that, what do you do with it? So you have to analyze the responses. So I'm just going to go through some synthetic examples and talk about in-holes, off-holes, edges, that kind of stuff like that. What it takes to model it, plate sources, that kind of stuff like that. Then I'm going to touch upon some of the initial discovery boreholes. So that would be 168 and then followed by 169. And then I'm also going to talk about a few holes and tell a story about the discovery of a high-grade gold-copper discovery. And then I'm going to finish off with a little bit of borehole Fluxgate here. So we've all seen this before, the surface data that was collected by Dave Coop and Alan Bowles here, indicating the, I guess it's not working, so I'm going to have to dual wield here. Indicating this deposit here, the Lalor deposit. And so from the modeling of the surface data, you ended up getting a relatively large tubular flat dipping conductor at approximately around 800 meters. So naturally what you do is you end up trying to drill the anomaly, and even if it takes a few years after, and you run some borehole EM on it. And so from what I've been told, there have been over 200 Crone borehole EM surveys that have been conducted at Lalor. Some of them have been repeats on holes with different survey parameters, time bases, maybe different loops. But for the majority, they were all conducted with the Crone Pulse EM system. So what I'd like to point out here is that a lot of these surveys, or pretty much the majority of these surveys, were carried out under sort of routine conditions. So this is all when you're trying to explore. So you don't really know what your source is, you're not really sure what to expect, but when you're planning your survey and you're planning your survey parameters, you want to maximize everything in order to get the best data possible. Just to know, it's always much easier to plan a survey and do everything you can and throw, different time bases, maximum current, and, put the best loop position out there to couple with your body when you know it's there. So just to note that, they didn't really know that it was really there. So the Crone borehole EM equipment is just the CDR2 receiver, the PEM transmitter, which can be used in a variety of different configurations. Just on its own, you can do parallel series, that kind of stuff like that. Then we have our standard induction coils. So there's a Z probe and an XY probe. And then we also have this RAD tool here, which basically makes some sense of your XY data after the fact and also gives you information about the whole geometry. And then you also have your Fluxgate here, which I'll mention towards the end. So in terms of borehole EM responses, just to be pretty simplistic, you have your in-hole, off-hole responses, edge. And modeling this stuff can provide a lot of details about your sources. So the size, distance, direction, its conductance, and a lot of this stuff, this modeling is done through Maxwell. And then you can also look at your step data as well, which I think Bob Fraser developed something with Hudbay on that. So just to start off, the Crone borehole EM coordinate system, we use this axial system. So your Z always follows the trace of the hole. So this is a section, so it's always following the direction of the hole. Your U, which is your X, is always perpendicular to the azimuth, so it's always sticking out. And then your V, which is your Y, which is going into the page here, is counterclockwise 9 degrees to your X. And then this is what it looks like in plan. So just to start off with in-hole and off-hole responses. So usually you get this from your Z data. And so the in-hole points to the center of the conductor. So this is actually when you've struck something that's conductive, and your off hole points to the closest edge. So looking at this here, you've intersected something, so this will be an in-hole response, and I'll explain what that is. And then out here, you'll be able to see this stuff around the borehole. You won't know exactly in which direction it is, but you'll know that you do have something off the hole there. So the XY data that you do afterwards ends up giving you the direction. And so the X will let you know whether it's above or below the hole. And then your Y will tell you left or right. So all this information together will be able to pinpoint the sources. So then we also have an edge type anomaly where you sort of struck something right on the edge there. So it'll start off in the Z in the early times as an in-hole response indicating the positives here. And then in late times will actually shift and go negative. So this is as the eddy currents collapse towards the center of the source. So, and just some XY data here. So this is just a synthetic example that I had done. You end up having a crossover here right where the anomaly is. And then the XY will point above and to the right of the hole. So another thing is that we do at Crone is the step response. And it's something that we do, and it responds to extremely high conductance targets. So you don't miss some of those things. And I'm just going to show a little example here where doing a step or looking at the step data can actually identify potential sources that might be missed by just looking at the off time. So in this example here, we have hole A, which ends up intersecting right here, and it intersects through basically less than 10% sulfide. So looking at the off-time data, you do see an in-hole response because you have intersected it, and you also do get a response that indicates above and to the right in the XY data. So now taking a look at the step data, we actually see that we have an off-hole response, and we actually are seeing something, or it's actually indicating that something is below and to the left of the hole. And looking at this, you can see that, you know, say off the hole here because you haven't intersected it, are massive sulfides, so the step is actually pointing in the opposite direction. So it's an extra valuable data set that might help you out, and you know, you might be missing something like this by just looking at off-time data. So moving on to borehole interp. So you kind of see what the responses are like, but you know, borehole interp is not always easy. So sometimes you get different types of responses in different channels. So whether you're looking in your early versus your late time or even your mid time. So, you know, trying to model early time data and getting a model out of it and then modeling the late times, they can be pretty different. Also, you can get mixed responses here. So, you know, you don't always have one source per anomaly. Sometimes you might have a couple sources and you end up getting a mix in between a bunch of different things. So modeling can become a nightmare pretty quick, especially when you're trying to model a lot of different plates. So this is just an example of some data. So you can see it's pretty complex, and you know, you don't just have one anomaly in the hole that you can sort of satisfy with one plate. You're probably going to need a few plates, especially to sort of, I guess, describe what's going on here. You know, sometimes you know, you take a look at it, your responses aren't always so clear. So it can be quite a hassle. So modeling this stuff and sort of looking at the detail and paying attention to the detail and knowing what it means can sometimes mean the difference between finding a mine or not, as I will talk about later, and I will talk about it now. So looking at Dub 168, which was the original discovery hole, I think Dave Coop was supposed to talk about it, but he sort of threw it to me. So it's the original discovery hole. So, you know, you can see that there's quite a few things going on here. You have something going on here, a nice crossover, and you definitely have some responses going on here, like some in-hole and some also off-hole responses and some crossovers in the X and Y, which will give a direction. And so it's looking at this data and modeling it and seeing what you get out of it and seeing if the plates that you're getting and the targets that you're getting are viable for further exploration. And so that's something that you have to consciously decide as you model. But the one thing that I will note here is that you see a buildup towards the end of this hole. And it was this that prompted them to deepen the hole. And so they saw that something was going on here, and they said, well, you know, let's deepen it, let's see what happens, see what this anomaly looks like. So they deepened it. I will note there is some overlap. This goes to 950. This starts off here. I had I believe 900. So you end up getting a nice in-hole response here at 1,000 meters below and to the left of the borehole. So this ended up being this discovery zone hit right here. Pretty big whopping anomaly. Get a nice crossover in the X, get a crossover in the Y. And then you also have this anomaly B over here, which is an in-hole offhole. I didn't show the early time channels, but it is an in-hole. And so I just used channels 20 to 24. And it was to the left and above the borehole. But this is the huge discovery here. So it was paying attention to detail in the beginning and seeing that response, building up towards the end, deepening the hole, which resulted in this. So next we're going to go to 169, and you see the same story here. You do have a response as well before, but you also see this buildup happening here, going from an offhole and moving towards an in-hole response. So again, the decision here was to deepen the hole and sort of keep going. And then so looking at the data, when they deepened it, you get a large in-hole at 970 meters, and the modeled extent was to be larger than 300 meters. So you end up getting a nice crossover in the X and the Y. So this is pretty textbook here. So this was another very successful hole just by paying attention to the detail and the buildup at the end and deciding to deepen it and keep going. So now I'm going to talk about this sort of gold-copper discovery here. I'm guessing it's this area here that extends to the north. And so as I was speaking to Alan and getting some data from him, basically this whole discovery here was basically attributed to Borehole EM. And so without it, they probably wouldn't have been able to see it. So this is a huge win for Borehole. So I'm just going to talk about the story, talk about 3 holes that led to the discovery of this hole. And so it starts off with Dub 263. So just going through the anomalies, you have an in-hole off-hole, so early times positive, late times going negative, and at 1100. And then you also have this in-hole off-hole approach at the end of the hole. So you can see it's positive in the early times and negative and starting to go negative in the late times. So I guess the decision was, well, let's deepen this hole, let's close off this anomaly here, let's see what's going on. We're probably not going to hit any mineralization, but, whatever. So they decided, so we'll look at the step here, also a step anomaly located in agreement with A and B. So you see the same things going on. So they decided to drill Dub 236 wedge 1. So again, you have a bunch of anomalies here. A, off-hole at 360, and B, C, D, E, and F. So you can see that there's a variety of different anomalies here. Some of them are pretty close together. But that's the thing, is you have to decide, okay, well, are these worth exploring or not? And so, see, D looks pretty good here. So I guess they decided, that's the one we're going to focus on. And that's at 1,330 meters. So slight above and to the right of the hole. You get a nice response here. Taking a look at the step, you can see all the step for all the different anomalies. B wasn't resolved so well. X was a little bit blown out by this here. Probably should have used slightly different channels, but you can see you do still get a nice anomaly from D here. So then they decided to wedge another hole. This is 263 wedge 2. And so you'll notice that there is an off-hole response here, A, at 1070, below and to the left. Not really much in the X here. Might be able to pick it out, but you do get something in Y here. B here, this is the hole that hit. This is the anomaly that hit. So it's an in-hole off-hole response at 1270. So the extent was modeled to be about 300 meters and is located above and to the right of the hole. So you'll note that the intersection is at 1270, whereas the anomaly was originally at 1330, I believe. Yeah. So the reason why it was hit up a little higher and they decided to drill it that way was because the structural dip played a role in this case. So this is a good story of where a little bit of geology and a little bit of geophysics comes together to find something quite spectacular here. So what they ended up intersecting was basically over 30 meters of mineralization, not necessarily high grade all the way through, or not necessarily massive all the way through, but high grade nonetheless. So looking at the step here, you get a nice step anomaly here associated with this anomaly. So since then, there's been a lot of additional holes that have been drilled. I'm just going to touch on a couple. This one here, 263W2 is the discovery hole here. And then you also get a few, I guess this is 265 wedge 1. And so you end up seeing that they drilled it off. Well, they were drilling, and they were drilling down dip, ended up still hitting. They've done a bunch of holes up dip, hit. But so this sort of proved that, you know, it was still sort of open to the north here. Another one was this one over here that hit. And this is 189. And you can see that, you know, it kind of still shows that it's maybe a little more open to the west than previously thought. So there's obviously been a lot more holes that have been drilled since then. So, you know, I'm just sort of commenting on the few that I see here. So it's been a very good discovery. So now I'm just going to talk about a little bit of B field data. A lot of people have mentioned it, just in terms of, you know, Fluxgates, surface Fluxgates, squids, that kind of stuff like that, showing the relation between dB over dt against B field. So this is a survey that we had done. We resurveyed a hole, Dub 178, with our Fluxgate borehole. And so we ended up using a different loop. We used a 1x1 here, whereas the original dB by dt survey just ended up using this loop here. So you can see that the data is really nice. This was done at 150 milliseconds. So even all the way through, the data looks pretty good. So comparing that to the dB by dt, this is all the channels in a pseudo log plot in Maxwell. So you can see that and also just to note here that the Fluxgate survey went a little deeper to 1,000, and this only went to 850. So you're not going to see sort of, maybe you might see the edge of this stuff in here. But anyways, you can see that the Fluxgate data is really good, really clean, and especially at a longer time base. So in this case, the Fluxgate looks better. You know, we're dealing with high conductance targets, so B field in this case would work a lot better. But it is interesting, and it is a good thing to note that, you know, don't throw induction coils out. You know, they have they're a broadband system, and sometimes, you know, you might be looking for things like stringers and whatnot, which may show up just in your early times, and dB by dt is very good at picking out those early times, whereas B field isn't quite as good as picking out the early time sort of anomaly. So you might miss something entirely by just doing Fluxgate in this case. So you have to sort of pick your instrumentation, and you have to pick all your parameters carefully when doing a survey. But you know, when you're just, you know, trying to find a mine, you're in that stage where you're just looking. You know, you try to do your best, but, you know, I know that I've spoken to Alan. He's attested to that there have been some surveys that they've done with the dB by dt induction coils that have picked up some early time anomalies that weren't necessarily visible when redone with a Fluxgate. So, you know, they're both very great tools for very different scenarios. So you have to be careful about which one you pick. So, and also with the dB by dt, you can still find high conductance targets using the step response as I had mentioned earlier. So the one thing I'd like to do is just to thank Hud Bay Minerals and Coop Geotechnical for providing me with a lot of data for this talk. It's sort of evolved over the last couple days with Coop giving me some last minute holes and whatnot. So I'd like to thank those two. And I'd like to thank the BCGS for giving me the opportunity to give a talk here today. It was my first one, and I hope I didn't blow it.
Questions?
Yeah. Yeah, which one here? On this one? Oh, let's see here. Well, the one that I spoke about, 189, over 8 meters, 9.2 grams of gold, grams per ton, 46.89 grams per ton of silver, 0.1% copper, and 0.05% zinc. And then for 265 wedge 1, intersected 1.6 meters at 1.28 grams per ton gold, 7.98 grams per ton silver, and 0.68% copper and 0.14% zinc.
All right, thank you very much.
Sweet, no questions.
All right,